recording. Get my slides going. Okay, so good morning, everyone. In case anyone doesn't know me or they watch the recording of this later, my name is Carter Yagemann. I'm an assistant professor here at the Computer Science and Engineering Department at The Ohio State University. And over the next hour or so, I'm going to be talking about cyber-physical systems and, more importantly, cyber-physical security. So the agenda for today's talk is I'm going to start with some background information to get us all on the same page of what do I mean by a cyber-physical system and the security of these systems. I'm then going to talk about how our lab or my lab got into this space of cyber-physical security by talking about how we found an exploit to crash a DJI Phantom 3 drone. And then I'm going to talk about how we kind of took a step back from that exercise and started looking at ways to automate and make more efficient the reverse engineering process for assessing the security of such systems. And then I'm going to wrap up my talk by talking about some future work that we've just started in this kind of broad green pasture known as fault injection attacks. So with that, let's get into a little bit of background. So what do I mean when I say cyber-physical security? And more basically, what do I mean when I say a cyber-physical system? So cyber-physical system is this kind of catch-all term that's emerged in the past few years to just describe or capture any kind of system where you have some kind of physical component and some kind of cyber component. So whether it's like a quadcopter or a self-driving vehicle or even stationary things like industrial control systems, if there's a physical and that physical is being interacted with cyber, it counts as a cyber-physical system. And when I talk about cyber-physical systems, I like to always point back to this figure that DARPA made about 2 years ago, because you'll see in this diagram, the physical is this huge purple box, and the cyber is just this little sliver of blue. And no, that's not a coincidence or an accident. That was a deliberate design choice when they were making this diagram. And the reason being was that they really want to stress the importance of that physical side when you want to understand the security and the weaknesses of a cyber-physical system. In some contexts, it might be convenient to think of a self-driving car as just a computer that happens to have wheels, or a computer that just so happens to have propellers. But when we get into the security and weaknesses of these systems, we really have to respect and treat that physical side as kind of a first-class citizen. And I think something that's helpful just to help frame our minds is to compare a traditional IT system like your laptop against a cyber-physical system. And what are the key differences? So in a IT system, the first big difference is that the hardware is centralized. There's something I can point to in your laptop and say that's the central processing unit, that's the main memory, that's the motherboard. In a cyber-physical system, as we're going to see in the DJI Phantom 3, they tend to be very distributed. There is no one thing you can point at as being like the center of the system. So that changes how we have to think about these devices. Another thing is that because IT devices have been around so long, we have very nice standardized interfaces for them. So you can pick any operating system in use today, and chances are it has a notion of a file descriptor, it has sockets, it has pipes, it has system calls, and those system calls might even adhere to kind of a shared standard like POSIX. On the cyber-physical side, much more heterogeneous. I mean, even just talking about the operating system, some of these might be using general-purpose operating systems like Linux. Some might be using specialized real-time operating systems. Some might have no operating system at all, and the program just runs directly on bare metal. So the interfaces and the resulting abstractions are much more varied and complicated to generalize. And then lastly, but probably most importantly, an IT system is ultimately user-driven. A user is trying to complete a task, and the IT system helps them do that, whether it's editing a Word document, browsing a website or what have you. In a cyber physical system, yes, there might still be a human in the loop giving some high level direction, but in the second to second operation, it's predominantly an environment driven system. So the quadcopter, it might be told by a human what coordinates to travel to, but in the second to second, it's using its accelerometer and its gyroscope to figure out its orientation and keep itself leveled so it doesn't fall out of the sky or crash into a building. And likewise, in an industrial control system, it's looking at the temperature and the mixing of various chemicals and making sure that the reaction is going on correctly. So in my lab, we take predominantly a reverse engineering role in this problem. So what we look at a lot is given limited information at the onset about the system that we're trying to assess, how do we go about this process of reverse engineering it? So how do we take one of these cyber physical systems and figure out what it interacts with, what are its capabilities, what are its vulnerabilities, and ultimately, are any of those vulnerabilities exploitable? And there's any number of motivations I could pull out of my hat to justify why this reverse engineering is important. But since New York Times decided to write an article about this at the start of March, I'll pick on the military relevance. So there's a really interesting article in the New York Times that was published on March 3rd, where a journalist was looking at the war in Ukraine and how the battlefield has changed from the beginning to where we are now. And at the start of the war, what we saw was something very similar to kind of World War I era doctrine, where both sides heavily entrenched, heavily barricaded, and a lot of the fighting and casualties were being inflicted through the use of heavy artillery. Fast forward to today, and there's actually a shocking quote in the article, which is that drones now account for 70% of the casualties on both sides of that war. 70% in only a few years. So the point being that, yes, war machines, traditional war machines still play a role on the battlefield, but they're less and less becoming the spearhead of the fighting. It's actually drones that are doing a lot of the actual casualty inflicting. So, not to get too morbid here, but you can imagine why, for example, government entities might be very interested and put a lot of priority in these kind of reverse engineering capabilities. And I promise later I'll give an industry one that's a little more cheery than this, but these are the times we live in. So, spoiler alert, my lab did not start in hardware security or cyber physical systems security. Traditionally, my background is in software analysis, so finding buffer overflows and use after free vulnerabilities and stuff like that. So about 2 years ago, when DARPA announced a program on improving the state of the art in reverse engineering these systems, my lab didn't really have any background experience in doing this kind of thing. So the way that we kind of dipped our toe into this problem was we took a DJI Phantom 3, which if you've never seen before, it's a fairly standard and popular commercial drone. And we basically just asked ourselves, okay, let's find an exploit that can crash this thing. We're not, yes?
Chinese made?
Yes, Chinese made. And there's some details about how we were able to do this because OSU is not allowed to buy, DJI drones. But that, we can talk about offline. But through means, we had access to a DJI drone, which we did not own. And we just asked ourselves, how could we crash this thing? And we weren't worried yet about being scientific about this or generalizing. We just wanted to go through the manual exercise of finding an exploit and then kind of learn from there. And basically, I want to take you along this journey because I think for those of you who haven't looked at this before, this is a nice kind of story to help understand the problem. So the first thing was to do a hardware teardown. So we disassembled this thing and we cataloged all the parts and photographed everything. And this is the first moment when we understood the difference of dealing with a cyber physical system. In a DJI Phantom 3, there is not one board driving the system. There are actually over a dozen boards connected to each other with various cables and ribbons and so forth. And each of those boards actually has anywhere between 1 to 3 processors on it. So there is no CPU, there is no motherboard. It's a heterogeneous distributed system all working together in concert to keep the drone in the air. And then we ran into the first challenge, which is that we wanted to focus on the firmware, so the cyber side of this, and how do we actually get the firmware from a reverse engineering perspective. So we're not the developers in this case. So over the years of Fire, we have built up our capabilities. So we now have means to actually just rip firmware with a pretty high success rate out of memory. I say we in a very broad sense, and I can talk about offline what we actually means. But yeah, nowadays we're actually pretty good at just ripping the firmware out of memory, but back then we didn't have those capabilities, so we kind of lucked out here in that DJI makes firmware updates available on their website. So we just looked up the latest firmware for the Phantom 3, we grabbed it from there, and as it turns out, there's already a vibrant community of tinkerers and hackers who mess with DJI firmware to do things the manufacturer didn't intend. So there was actually already a lot of information online for how to unpack this firmware update and basically get each of the individual firmwares and the kind of metadata that tells you which binary blob goes onto which processor. So this one we kind of lucked out on. So, okay, we have these binary blobs. How do we do any kind of program analysis on this? Like, how do we build control flow graphs and call graphs and data dependency graphs and the things that us in the software space like to use? So the first thing we discovered was that these binary blobs are completely stripped and headless. What I mean by that is that if any of you have done program analysis before, you've probably done it on a user space program. And in any kind of portable executable, you usually have this header, either like a PE or a macho or an ELF, and that header tells you a lot of important metadata about how to run this program. It'll tell you what the machine architecture is, it'll tell you how to load it into memory. When you are dealing with these firmware and reverse engineering, a lot of times you actually don't have any of that header information. You literally just have a blob of bytes and some of its code, some of its data, and you have to disambiguate it. So how do we figure out like what is the architecture, what is the entry point, how do we load this thing into virtual memory? The answer, at least for us, was that we looked at the hardware. So in our case, we decided to, because we were trying to move fast and quick here, let's just focus on one small board in the Phantom 3 that we think is important. So we picked out this one because it seemed to have like some camera on it and something above it. In hindsight, what I can tell you is that this turned out to be what DJI calls the visual positioning system. So in a drone, especially when you're maneuvering at low altitudes close to the ground, GPS does not have enough precision for the drone to safely navigate itself. So at low altitudes, what it actually does is it uses a camera pointed at the ground combined with a sonar, like an ultrasonic sonar rangefinder, to keep track of how low it is to the ground, how it's moving over that surface, and this is used to do things like stabilize the drone during takeoff and landing. So if we look at the left side, there's a camera, there's an ultrasonic rangefinder, which is the interface to the physical world. And then if we look at the back side of it, there's actually two processors, a ARM Cortex-M0 and a slightly bigger ARM Cortex-M4. Without getting into all the technical details, it turns out that there was some information about this board available online that allowed us to get to kind of a crude functional diagram of how these pieces fit together. And what we were able to figure out is that the camera goes to that larger processor and the ultrasonic rangefinder goes to the smaller processor on this board. So in the top right, we have the microphone and the speaker for sending the ping and getting the response. That goes into a little bit of hardware logic to calculate the delta in that send and receive. And then that goes to the M0 to compute a distance from there. And then it actually passes that up into the M4, which then combines it with accelerometer, gyroscope, and camera information. And then this ultimately goes upstream into the electronic speed controller, so adjustments can be made to the props. So once again, because we just wanted to find the lowest hanging fruit, we decided to focus on the sonar because it was a smaller processor. We noticed the firmware blob was smaller, so we figured that this was where we would have the highest chance of success. So bootstrapping the actual analysis of this firmware from those photos and figuring out which processor this firmware belongs to, we could then read the serial number off of that chip and find the data sheet for it. So that's how we figured out that this was a Cortex M0 and that's a 32-bit ARM processor. We still didn't know, and in fact, we never did find where the entry point of this binary blob is. But what we were able to do is using kind of standard heuristics that we use in program analysis, scan the bytes of this blob and use heuristics to guesstimate where functions were and then start to stitch those functions together. And then in terms of the base address, this we also never truly figured out, but because we had the data sheet for the processor, we knew where in memory was like the code region. So we just plopped the firmware down at the start of the code region and basically just gave it a shot. And what we ended up with was a call graph like this. So if you haven't seen a call graph before, each node represents a function and each edge expresses a caller-callee relationship. And don't worry about the details of this call graph. It's not important for this talk. But as a software analyst, when I see this gives me pretty good confidence that we're disassembling this firmware correctly, because I see a bunch of nodes for different functions, and more importantly, I see the nodes are fairly well connected to each other. Usually, if you're making a bunch of mistakes and you're mistaking a bunch of things as functions that aren't actually functions, you'll end up with a graph with very few edges in it, because you're not actually disassembling valid instructions. So when you see kind of a nicely connected graph like this, there's probably a few mistakes in it, like in the top right corner where there's like some functions not connected to anything. But in general, this was, this was a good enough shot for us to move forward. So then, okay, we have the pictures of the board. We're able to distinguish the code from the data. We know that we're dealing with a sonar system here. What are the attacks that you can do to a sonar system? So whether it's sonar, radar, any of these kind of techniques that can be used for distance estimation, the three fundamental attacks you can do are jamming, spoofing, and cancellation. So jamming is where you just generate a bunch of noise, so the sonar sends out a ping and it's never able to pick up the response because you've just flooded that frequency. Spoofing is where you try to time a fake ping to cause the sonar to mismeasure its distance. And then cancellation, which is probably the trickiest, is where you calculate the inverse wave and you send an inverse wave at just the right time, and kind of like two waves on a lake, they actually cancel each other out. In any case, regardless of which kind of attacks, which one of these attacks you want to attempt, what they all have in common is you need to know the frequency of the sonar system. I mean, I guess in jamming, you could just try to flood a huge range of frequencies, but it definitely helps if you know what frequency it is. So since we were able to disassemble this code, was it possible for us to automatically pull out of the firmware what frequency the sonar was using? And the short answer was yes. And the way that we did it was that because we had the data sheet for the processor, one of the important things to know about generating waves for sound or what have you, is that because generating a particular frequency is a very time-sensitive operation, you usually don't implement this in software. Most processors will have built into them a peripheral called a pulse width modulator, and basically you program the PWM and it will generate your sine wave for you. And what's nice about that is it means we can just look up in the data sheet the definition for the PWM's frequency. So we don't have to worry about all the variables here, but basically all these variables correspond to fields in certain control registers. So if we can find the code that configures the PWM and we can recover what values were written into all the fields, we can plug it into this formula and it will tell us the frequency. So we used a technique called symbolic analysis to do this. I don't have time to go into the details of how that works in this talk, but I'm happy to talk offline about how that works. But in short, we were able to recover the values written when the firmware initializes the hardware or configures it. And then we actually did run into one funny kind of gotcha, which is that in this processor, the pulse width modulator requires a base frequency, and it can either get that from the processor's internal clock, or it can actually get it from an external clock. And when we recovered the values, we discovered it was using external clock. And that's actually because the processor has to do some synchronization with that upstream M4, which I can get to offline. But long story short, we went back to the photos, we scoured over the hardware, and we found, lo and behold, in the top right corner, this serial number corresponds to a quartz clock crystal. So that gave us the base frequency. We completed the formula, and we got an output of 40 kilohertz. And we didn't know this at the time, but 40 kilohertz is actually kind of the industry standard for these ultrasonic rangefinders. But it was cool to see that we organically arrived at the correct number without that prior. Yeah, exactly. So we organically arrived, and then it turned out that that was a common number. So that gave us really good confidence that we did this right. So that was awesome because we were able to recover a frequency without having to sit there and actually tinker with the hardware, just with a couple of photos to help us identify some of the components. So at that point, we were going to set up this attack and try to crash this DJI drone. But then in some of our literature review, we actually saw that a lab in Israel had recently crashed a Mavic Pro from DJI using sonar spoofing. So that got us thinking, hey, wait a second, these are both DJI drones. We just saw the Mavic Pro will crash during takeoff or landing if you spoof the sonar signal. Can we actually figure out the Phantom 3 is vulnerable without having to conduct the test in real life? And the answer was actually yes. We were able to verify that the Phantom 3 has the same vulnerability without doing the attack. And the way that we did it was we looked at some photos of the Mavic Pro, and lo and behold, we found the exact same hardware subcomponents on two positions in the board. It's a little funny that the Phantom 3 only has one set of this hardware and the Mavic has two sets, but it becomes a little bit clearer when you then look at the flip side of the board where you have one ultrasonic rangefinder and two cameras. To this day, we haven't had time to go in and figure out why it's using two cameras and two separate VPSs. But regardless, because they share the same ultrasonic rangefinder, and it turns out that they use the same firmware for controlling these components, it follows that it will have the same problem and same vulnerability to sonar spoofing.
Can you speculate why they would use two?
Yeah, the short answer is we really don't know. And we haven't been able to figure out through reverse engineering the firmware because it's two discrete VPSs. So they're not even
depth perception.
I don't know because we haven't been able to find anywhere where they coordinate with each other. Similar to the Phantom 3, it goes upstream to the electronic speed control, and maybe somewhere in there it aggregates the information, but we didn't go to that level. Yeah, the firmware gets a lot bigger at that part of the flow, so we haven't reverse engineered it.
So Mavic is a higher end tool.
I actually think the Mavic is a cheaper drone because if you look at it, it's smaller. And I know that's not a great correlation. That said, it does have two cameras instead of one, but I don't think it has like the whole like camera gimbal system that the Phantom does. So yeah, I guess it's a little complicated as well because the Phantom is like meant for like photography and stuff. It has a nice HD camera on a gimbal. The Mavic does not. Like it's just a small kind of drone that navigates itself around. But as it turns out, and this makes sense, DJI doesn't reinvent their hardware or software, they just reuse it. Once they have a component that works, they plug it into everything. So just like how a library in a piece of software can open a whole suite of programs to the same vulnerability. Think like libpng, for example, which is in literally everything. The same thing applies to drones. There's a lot of reuse of hardware and software, so a vulnerability in one actually is transferable, or at least that's what we're seeing. Any other questions before I kind of segue here into more researchy stuff?
Were they using a real-time operating system on any of these?
So the visual positioning system was bare metal. As you get high enough up the stack, you eventually reach the autopilot, and that will be running. I believe I'm pretty sure we're pretty confident that DJI is using some kind of in-house variant of PX4, and I think we have verified that they're probably using NutX, so that is a real-time operating system. And then usually above that, there might be some kind of like a processor for like a web interface or like ground control. And at that point, you're usually in like a Linux environment. So that's what makes cyber physical so interesting is you go from bare metal to NutX to Linux. It's a very heterogeneous environment. Any other questions? All right. So, like I said, that was just our kind of dipping our toe into this space and kind of learning the lay of the land. What we then wanted to see was, okay, how can we do this better? What are the problems in this space that that we can create kind of novel solutions for? And one of the things we understood from this exercise was that interface between the software and the hardware peripherals is extremely important to understanding a cyber physical system. The fact that we knew that we were dealing with a sonic rangefinder is how we had our hypothesis that we could jam, cancel, spoof. And that's ultimately what led to our finding of the exploit. So how could we do this better? For example, how could we build a system that's a little less reliant on data sheets and less reliant on that functional diagram of how the hardware components fit together that we kind of lucked out when we were searching the internet and the hacker communities. So the dream in the system that we call ProtoReveal is to try to, in our firmware analysis, go from a situation like on the left, where we have this firmware, we're able to see that it's touching all these peripheral interfaces in what we call the MMIO region, but we don't really know what it's doing, to something more like on the right, where we can actually clearly determine what are the interfaces, what are the protocols being used, and ultimately what are the devices, the peripherals on the other end of that. So I2C connected to some sensors, UART connected to a GPS, electronic speed control connected to a series of motors. How do we automatically, through firmware analysis, get to the right side? So just as a full disclosure, this work is still a work in progress. We have achieved the first step of our goal, which is being able to recover the protocols being used, which is what I'm going to predominantly talk about here. We are also starting to have initial success in being able to fingerprint and predict the peripherals from a class of like 7 categories. We're at around 72% accuracy right now, which is way better than random guess. Random guess is 1 over 7, but we still think there's work to be done here before we're ready to talk about that part. The first part is a paper that's currently under submission. The second part, we hope to have a paper soon. In the interest of time, I won't go into all the details and kind of secret sauce of what we're doing here, also because the paper is still unpublished. But just to give you a high-level idea of what we're doing, we're combining program analysis techniques with machine learning techniques. probably not a huge shock to you. So what we're doing is we're taking this firmware, we're applying our automated techniques, predominantly symbolic analysis, to recover the control flow, to recover the data dependencies, and we're tracing that down to the point in the code where it accesses one of those interfaces in the MMIO. Once we know what code and data corresponds to which interface, we can then extract some features that characterize what that code and data is doing with that interface. A lot of these features are inspired by prior work on trying to do like code similarity detection and stuff like that, but we also have some novel features thrown in there that I can talk about offline. But basically, once we have all those features that characterize this slice of code and data, we then feed that into a machine learning classifier to try to predict the protocol. Something interesting here is that even though these days the hot thing is deep learning, we actually opted to go for a random forest, which is kind of a classical machine learning model. And the main reason we did that was because of data set size. One of the challenges of working in this space is unlike like image recognition or stuff like that, there's just not a lot of data available for this kind of learning problem. So my student Bayan, shout outs to her, basically had to spend months building and labeling data in order to attempt to train this system. So classical learners are generally better on smaller, sparser data. So that's why we use a random forest there. So once again, huge kudos to Bayan. She actually went through 412 firmware from 6 different manufacturers, 2 machine architectures, ARM and MIPS, 35 microcontrollers, and 82 different protocols. That was another thing we learned, was we thought that there would be a couple of protocols. We did not understand just how many protocols there are. Yes?
So those were custom roll protocols or kind of standard in some sense?
Yeah, so they were all standard in the sense that information is available online that defines what they are. And like in the data sheet, it will tell you the name of that protocol. Yeah, sometimes, so there are actually 2 kinds of peripherals. There are internal peripherals that are inside the chip, and then there are external, which are outside the chip. External peripherals almost always use some kind of known protocol. It's when you start dealing with the internal peripherals that you might run into a proprietary protocol. So by sticking to ARMs and MIPS, we were able to largely avoid this problem. If you start to get into some things like Texas Instruments, sometimes they use ARM, sometimes they use like a proprietary ISA, instruction set architecture, and then it gets a little shady. So for example, there's a TI battery manager that we still don't know what the protocol is for how it communicates with the battery to make sure it doesn't catch on fire. But yeah, anyway, Bayan built this giant data set. It took her months to do it, but the benefit of it was that we were able to achieve 92% accuracy across 82 different protocols, which was probably the craziest part. This is an 82 class classification problem. So yeah, I'm going to stay pretty high level there, once again, just because this isn't published yet. So that's kind of where we are. I know that's super high level, but does anyone have any questions about that before I kind of move into the tail end of this talk?
The protocols, did you do any research? Just look at them for their security or how vulnerabilities? I'm just curious.
Yeah, so for the vulnerabilities, you have to start getting into the semantics. So you really need to get into what are the payloads being sent back and forth. And to do that, it really helps to know what kind of peripheral is on the other end. Because like a CAN bus or an I2C, yeah, anything can be on the other side of that. So that's really where the second part that we're still working on is really going to be valuable, because there we can actually say this is a sensor, or this is a GPS, or this is a motor. And then with that combination of, we know the protocol, and we now know roughly what the semantics of the payload is, now we can start to say like, oh, we've seen this kind of motor before, we've seen this kind of code before, we've seen a vulnerability previously, maybe the vulnerability applies to this instance as well. So we're always thinking about that Mavic Pro Phantom 3 example of like transferability and being able to form these hypotheses of exploits to really narrow down and target our search. But yeah, all work in progress. Any other questions? All right. Then for the last part here, I'm going to segue a little bit, and I'm going to talk about some work that we started up about 4 months ago. So, but I think this is a really cool topic. So hopefully some of these students will find this cool as well. Let's talk a bit about fault injection attacks. So if you've never heard about a fault injection attack, basically your hardware, just like your software, can have bugs and limitations in it. Under certain conditions, hardware can encounter faults, which is where a misbehavior occurs. And most of these faults just cause hard lockups of the system, so you can't really do much with them. But every once in a while, under just the right conditions, you can get a fault that causes a instruction to not do what it's supposed to do, and yet the system continues running. So using a hardware fault, you can actually do really weird things like cause an instruction to skip, or cause an arithmetic operation to output the wrong value, or cause a register to just abruptly reset to 0. And attackers deliberately control the injection of these faults in order to craft exploits that can be used to do things like break crypto by corrupting the key right before it's used, cause formulas to miscalculate, or even just bypass security checks, such as in secure boot. And yeah, I'll leave it at that for now, but basically this is the art of fault injection, attack, and defense.
Would that be like a Stuxnet and the Iranian stuff, telling that motor to spit up until it blows up?
So that's different because that's being done through the software. In a fault injection, you're essentially exposing the hardware to unexpected energy or absence of energy, and you're pushing the hardware into the boundaries of its operating condition. And sometimes you can get right on the boundary where it doesn't work correctly. It experiences a fault or anomaly, but it doesn't just outright lock up all the circuits and cause a hard crash. So yeah, I can talk more offline about like how that occurs. It gets into the physics of what we call like transient execution and some superposition stuff. It's a really interesting space because there's a lot of research at like the nuclear physics level, because this started with anomalies happening in space due to space radiation, and over time has moved into something that people actually weaponize as an attack. As an example of a motivation, like I said, I promise I would only use one military example, so let's use an industry example now. The Nintendo Switch. So when you buy a Nintendo Switch, it comes to you in a locked down production mode. So one of the things in there is it has secure boot. So secure boot will only let you boot firmware signed by Nintendo. And the reason that they do this is because if you have unfettered access to rewrite the firmware, you can do things like rip video game files directly off the file system and use that for piracy. You could start to attack the eShop and all sorts of other bad things. So for many understandable reasons, Nintendo only wants you running their code on their hardware. As it turns out, when the processor is booting and it's doing the secure boot checks to make sure that this firmware is a uncorrupted, correctly signed firmware, there is actually only one conditional branch, only one point in the program where it checks whether it is in secure boot mode or whether it's in the unlocked debugging mode. And as it turns out, if you drop the voltage for just that instruction, or using a electromagnetic probe, if you shock the right transistor right on that instruction, you will skip the check, and the Nintendo Switch unlocks itself. And then from there, you have root access. You can reprogram it or do whatever you want to it. So yes, you can imagine why the military cares a lot about fault injection attacks, because of stuff that comes off the battlefield that they want to reverse engineer. But you can also understand, how like industry people who make and release hardware don't want people to be able to just bypass security checks. So like I said, we've only been working on this for about 4 months, so I'm going to kind of raise more questions and insights than answers. But what's interesting was that we started by doing a large literature review of like what is the state of the art in fault injection attack and defense. And what was interesting here was that we actually had to go way outside of our wheelhouse to answer this question, because There is research in like the physics discipline. There's research in nuclear engineering. There's research in hardware security, software security. Everyone has a different perspective on fault injection attacks, like why they occur at different levels of the system. But in the interest of time, we could roughly bucket the understanding of this problem into two domains, which is the hardware side and the software side. So if you want to anticipate where fault injection attacks can be exploited and ultimately defend against them, the hardware people, they tend to look at the circuitry. And basically, there are ways that you can model the circuits to anticipate how a fault will propagate through a particular circuit. And then they tend to defend against these faults by adding more stuff into the hardware. So for example, you can add a circuit to smooth out the voltage, so that way abrupt fluctuations won't cause a glitch. Some really high-end hardware will even do things like put photosensors onto the board. So if you try to shine a laser at the transistor, the photosensor will trip and the board will reset itself. So there's all sorts of these kind of hardware level defenses that try to stop you from achieving a controlled glitch. And then on the flip side, there's the software side. So as you can imagine, those hardware techniques they're expensive. They have trouble scaling to like an entire program. So on the software side, what they tend to do is they abstract away all those details. They just assume they have some kind of logical model of a fault. So like assume I can flip a bit or assume I can skip one instruction. Where's everywhere in the software where I could use that primitive to achieve an attacker's goal. And then usually they use various forms of error correction and kind of redundant checks to protect those critical code regions. But what we notice, which is really interesting, is there's actually a huge gap between these two sides, the hardware people and the software people. And I think the easiest way to illustrate this is to compare it to how we reason about software vulnerabilities. So for example, if I have like Nginx web server and I want to find an exploit in it, the first thing I'm going to do is look for bugs in the program. So maybe, for example, somewhere in the code it uses strcpy, and because strcpy doesn't have bounds checking, maybe there's a place where a buffer overflows. And then once I have found this particular buggy use of strcpy, I can start to characterize what is the primitive, what is the capability I get from that. So for example, I know it's an out-of-bounds write. I know the out-of-bounds write starts at the end of the buffer. I know that the things I have to write have to be null bytes, ending with a final null byte. So basically the last character has to be null, but all the characters before can't be null. So I can really accurately describe what are the constraints that bound this primitive. And then I can go looking in the program to try to figure out if I apply that primitive somewhere, can I achieve a goal such as reaching a certain instruction? If we look at the fault injection side, there's a big technical gap there, which is that at the hardware level, people are really good at saying or explaining how like a photon beam from a laser can excite this transistor. And if you think of the transistors as a directed acyclic graph, this is how that fault will transfer across the circuit. And at the end of the circuit, I get this incorrect output, this bit flip. And then there's this big nebulous gap, like the microarchitecture and the software and the instruction set architecture. And on the other end, we have the software people who say, assume I have an arbitrary bit flip. And because those constraints aren't being modeled up the stack, what ends up happening is that when you then try to, at the software level, with your very over-approximative fault model, try to figure out what's vulnerable, you basically label 92% of the program as vulnerable and exploitable, and then the mitigations all become extremely expensive. So this is the gap that we're trying to help fill in our work. So the system that we're working on right now, and most of this is still work in progress, but we're trying to take the practice of fault injection attacks from an art and turn it into a systematic, repeatable science. And the way that we're doing that is with a combination of a hardware test bed plugged into a program analysis. So we take in a target device, we load onto it some benchmark firmware, and then we expose it to lots of different clock glitches, voltage glitches, and hopefully in the future laser and electromagnetic glitches. And we basically see what happens to our benchmark firmware. When do bits flip, when do instructions skip, stuff like that. And by diagnosing when and how the fault is occurring, we can then extract that into a fault model that can then go into our emulator, our software emulator. So we basically have an ARM emulator that will take this fault model, take a target program, and it will find for you every candidate exploit up to N faults. We can then take those exploit candidates and we can turn those into recipes, basically, that we then feed back into the hardware laboratory. So we tell the glitching hardware, hey, we believe this exploit occurs. We believe, this is roughly the parameters and the timing that you need. Go fuzz in this kind of part of the search space and tell me whether an exploit actually occurs. And if it does occur, we now have a repeatable recipe for how to glitch this particular software-hardware combination. So our hardware setup is really basic right now. We're starting out with something called the Chip Whisperer, which is a really great kind of $600 kit for clock and voltage. So this is an example. We have the Chip Whisperer here that does the glitching. In the middle, we have kind of a breakout board that allows us to interface with the target device. And on the right is our current target device. It's just a very simple 32-bit ARM processor on kind of a minimalistic board. And at the hardware characterization level, we end up with things like this graph on the right. So what this graph is showing, just as a proof of concept, are all the various settings for basically timing and duration of clock glitches. And the green marks are when no fault occurs, and the red marks are when a fault occurs that doesn't crash the system. So basically, we are finding under what conditions this fault occurs, and then we're still working on the process of distilling this into a fault model for the emulator, which is then going to tell us for a particular program where can we apply this. So yeah, that's the last slide I have. Like I said, still very early work, but we're definitely interested in collaborators if you find this topic interesting. And I just want to give a quick shout out to my students, Bayan, Patrick, and Fawn, whose work appeared in this presentation. So with that, I'm happy to take any final questions.
So in your first part, you talk about firmware analysis.
Yes.
How often do you see those firmware gets obfuscated?
Yeah, so especially when we're ripping firmware directly out of memory, we actually very rarely encounter obfuscation. And part of the reason, I think, is because of the real-time constraints. So since you're dealing with a physical system, the system has to maintain a certain frequency of updates or processing of events. We tend to not encounter that much obfuscation. If there is obfuscation, it's more at the hardware level. So, for example, the memory will have like encryption built into it. But with fault injection techniques where you can, skip instructions and disable a lot of that stuff, we have ways where we can extract the unencrypted form of it. So yeah, most of the protection is at hardware level, not actually software level.
So you have like 400 firmware. Maybe it's good to do a measurement study to see how.
Yeah. So one of the things that we're really interested in and we're slowly working through is we're doing a measurement study of drone manufacturers. So we want to see what is the code reuse and hardware reuse across drones within a manufacturer, drones across manufacturers, and the open source community. And that's why, we're pretty confident, for example, that DJI is actually using some kind of in-house variant of the PX4 autopilot. But yeah, that's all still a work in progress. Yes.
So yeah, the software commonly used. I mean, are you compiling or are you just kind of matching on the bit streams that you're seeing?
Yeah. So we are doing disassembly. And usually once we know the machine architecture, we can linearly scan through the bytes and look for things that look like the preambles and postambles of functions. And other work defends that this is actually like over 90% accurate, these kind of linear scan techniques. So similar to like what you would see in an IDAPRO or GIDRA, that's how we're finding the functions. And then once we find functions and they're outputting valid instructions, we find the call sites, the return sites, we start to stitch them together, we find the accesses to the MMIO, and that's how we bootstrap the firmware analysis.
Have you looked at how the firmware packages change over time for a given manufacturer?
Yeah, so we are looking at that, but yeah, also unfortunately work in progress. Yeah.
And what's kind of the question you're trying to consider in that?
So ultimately, what we're interested in is the transferability of weaknesses. So given a weakness in one drone, what is the probability of that weakness existing in other drones from the same manufacturer, and even potentially across manufacturers, because they're all feeding from the same open source community as kind of their starting point. Yeah. Any other questions? Yeah, Chris.
That's sort of a high level cover. I think just try and wrap it all together, right? The exploit is really on mass production of whatever hardware.
Right.
Then all of these things. I know there's a push for diversity in software. Right?
Yes.
So you were talking about the gap, right? Part of that gap is because there may be all kinds of things people are doing
Right.
to make software reliable. Well, is there a counter on the hardware side? Have people thought about diversifying the chips that they're using in these systems, even if they have the same external interface, but maybe they're a little different?
Yeah, that's a really good question. So the answer is kind of yes and no. So one, a lot of diversity does happen in the hardware, but it doesn't happen as a security strategy. It just happens as a pragmatic getting the work done. So for example, when we tear apart like a rover, we're going to see like ARM chips talking to AVR chips, talking to what is it called, Extensa chips over a CAN bus. And that's just because, those are the components that happen to work. On the more kind of like security side of the problem, something that I've learned is that hardware is hard. If you think it's hard to get a software to run correctly, it is a whole nother level of pain to get a hardware component to run correctly. And you have, tape out and fabrication. It's also way more expensive. So the challenge with like security through diversity is that in the hardware space, it is exponentially more expensive to try that than it is in the software space. So yeah, can you do things like, for example, make 3 systems and then have the systems do majority voting? So that way a exploit, working on one probably won't work on the others, and then you'll catch that through the majority vote. Yes, you can do that. We definitely see people try that on the software level, especially in the government space. It is harder to do it at the hardware space. Yeah. Yeah. Vimal.
Kind of related to that, but like a couple of years ago, I know like seen research that Mattel was doing, right? Like, but there were like counterfeit chips, right? That had
Yes.
the same lid and other stuff that would make it look like it's an ARM
Yep.
chip, but then really internally it's something else. Now, probably not showing up in like a DJI Mavic, but like in a missile or some other
Yeah.
things, there's like all sorts of other. Like, do you see any like synergies there? Or
Yes.
maybe, like,
No, yeah, there are actually, in fact, there are such strong synergies there that on the FIRE program, my lab collaborates with Battelle, and the team that I collaborate with worked on that chip counterfeiting problem. So actually, the way we started our capabilities on the hardware side was we took all that institutional knowledge from Battelle on chip counterfeiting, and even actually some of the equipment, and we translated it over to FIRE. So for example, they already had a large database of components. So Battelle, I can say this because this is publicly available on the internet, they have a system called Rakes where they can basically put a component into this kind of jig, and then it sweeps over it with different cameras and infrared sensors and stuff, and it actually automatically starts to identify all the components on that board. And now they actually have X-ray capabilities, so they can start to subsurface image and start to trace all the traces through the board. So they basically build our hardware bill of materials, and then here at OSU in my lab, we focus on the software side. So what is that hardware doing in the cyber domain.
Are they involved in helping kind of analyze the hardware?
Yes. So to get back to, I forget whose question it was of how we got a DJI Phantom 3 when we're not allowed to purchase from Chinese manufacturers. They had it laying around. And they helped us with the photography and the teardown.
Nice.
Yeah. Yes.
So, in the both injection tag talk about, like you mentioned the energy tag is one of those. Do you have more examples of this both injection tag?
Yeah, so the 4 ways that people do fault injection attacks right now are clock glitching, voltage glitching, electromagnetic injection, and laser injection. So with voltage, you basically mess with the timeline or the deadline in the propagation of signals. So by messing with the voltage in the clock, you can basically cause the hardware to move to the next cycle before all the signals have correctly propagated through the circuits. And that's when you get things like a bit or a byte reset. On the electromagnetic side, what you're basically doing is using electromagnetic field. You're actually generating a small electrical shock inside a circuit somewhere within your chip. And at just the right time, you can excite a circuit and cause a bit to flip that way. Yes.
It strikes me that your timing has to be pretty exquisite in your physical access.
Yes. So, for example, I have a friend who just glitched a Apple AirTag to unlock the secure boot. It took him about 2 weeks to set up the rig and 3 days of electromagnetic glitching to get to unlock. So that's the kind of time frame we're looking at. So.
I'm impressed that it was that short.
So what helped him was that someone online had glitched another device that had the same processor in it, and it had the same secure boot firmware in it. So that kind of gave him a rough idea of where it was. But even knowing all of that, it still took him 3 days of sitting there shocking it with a probe automatically over and over again. So that's yeah. Well, it was automated, so the hardware was doing the work, and he was just waiting. But that's part of the motivation for a workflow like this is to get more systematic with that, because he was basically just going off gut feelings and what he was reading in blog posts. It was very much more of an art than a science. So yeah, hopefully with this we can actually explain scientifically what actually happened that allowed him to do that and narrow the search space. All right. I think we're out of time. The next class is probably outside.